In the middle part of the 19th century, a man named Christian Doppler noticed that objects that emitted sound would produce either a rising or falling pitch to an observer, depending on the movement of the object relative to the observer. For example, an object which was producing a sound when moving toward an observer, such as a train, would produce a higher pitched sound as the object approached an observer. Likewise, a lower pitched sound would occur when the sounding object moved away from an observer. We know this today as the Doppler effect. Late in the 20th century, we merged radar technology with the Doppler effect, and we came up with Doppler radar, which is currently on your screen. Moisture shows up on Doppler radar much like it does on traditional radar, with one large exception, which makes Doppler radar superior. The Doppler radar unit detects the direction in which the moisture is moving relative to the Doppler unit itself. For example, moisture heading toward the Doppler radar may appear green, while moisture or precipitation heading away from the Doppler unit may appear red. The different colors tell meteorologists much more information than traditional radar can produce. In fact, it is the only tool that can be used outside of direct human observation to detect a funnel cloud or tornado. That is the hook image you see highlighted in this Doppler radar image. It is important to note that Doppler radar has no computation or compensation built in for the direction in which the signal is returned. In other words, an object moving toward the radar unit will shift the image towards green if the precipitation is moving toward the unit itself. It doesn't matter if the returned image is to the north or to the south or to the east or west. The Doppler radar unit is stationary and treats all returning signals alike, regardless of the directional source of the returned signal. And thus, with the spinning ball Earth that we are told exists, we've got a big problem. You see, if the Earth is rotating at somewhere between 750 to 1,000 miles per hour to the east, depending on the latitude of the radar unit, the Doppler effect would be totally negated by the Earth's rotation. Any echoes from the west would necessarily be moving away from the Doppler unit at 750 to 1,000 miles per hour, plus or minus the actual speed of the moisture that's moving itself, while echoes to the east would be rushing toward the radar unit at the same speed. All the other angles in between would create an almost infinite and nightmarish computation for the radar unit to sift through in order to make sense of the echoes received. The bottom line is, there is no computation or correction for any Earth movement whatsoever. The radar unit interprets all echoes the same, regardless of the compass direction. Doppler radar would be a total impossibility on a moving Earth. It simply would not exist. It would not and could not work if the Earth is a spinning ball.